Section: Introduction. In this section, we explore the exciting area of editing and animating portrait photos within computer vision. We note that researchers have developed various algorithms for tasks such as relighting portraits, manipulating facial expressions, and changing appearances, like hair color or adding accessories. For animation, we focus on tasks like transferring animations from one video to another or creating synthetic talking heads from audio. To achieve these tasks, we rely on advanced deep generative models, such as GANs and diffusion models, which are trained on extensive datasets of facial images and videos. From our observations with early models like StyleGAN, we see that these methods can create incredibly realistic images of human faces. The recent approaches in image editing and animation typically use a pre-trained generative model and learn to adjust the generation based on additional signals, such as lighting or audio. However, we identify a limitation in previous methods, which primarily focus on generating the visual appearance of faces, potentially restricting their applications. In our work, we demonstrate that learning both the appearance and depth of faces together can broaden the possibilities for portrait image animation. We propose a new architecture that simultaneously learns depth and appearance, emphasizing the importance of ensuring that the generated depth map aligns with the generated face image. To implement this, we introduce a diffusion-based portrait image generator that builds on stable diffusion but is tailored to learn this joint distribution. We utilize a reference network to extract the identity from an RGB reference photo, guiding the image diffusion process. Our model processes a 6-channel input image, which includes separately noised RGB and depth images, ensuring a strong correlation between the outputs. We train our model using a mix of studio-captured facial images with accurate 3D geometry from a facial scanner and real-world facial videos with approximate 3D geometry. This combination enables our model to learn precise depth generation and adapt to outdoor environments. Once trained, our model can be used for various applications, including generating paired RGB and depth images, performing channel-wise inpainting for depth estimation, and artistic control over face image generation. Additionally, we can relight the face images using normals derived from the depth images. Our model also extends to creating audio-driven talking head videos, maintaining consistency in appearance and depth throughout the performance. Our contributions include a novel architecture for joint learning of depth and appearance, a new training scheme for paired image and depth maps, and demonstrations of various applications in portrait manipulation. In the related works section, we discuss diffusion models for character animation, highlighting their adaptability and the advancements made with large pre-trained models like Stable Diffusion. We also review how diffusion models have been applied to geometric estimation tasks, including depth and normal estimation. Furthermore, we examine the progress in audio-driven talking head generation, noting that while many models focus on facial movements synchronized with audio, our approach uniquely integrates 2D and 3D animation using 3D priors from pre-trained diffusion models. Section Summary. In this section, we explore the advancements in portrait photo editing and animation using deep generative models, highlighting our novel architecture that jointly learns both appearance and depth for enhanced applications. We also discuss the integration of our model with existing diffusion techniques to enable tasks like depth estimation, portrait relighting, and audio-driven talking head generation, demonstrating its versatility and effectiveness in various scenarios. Section: Method. In this section, we discuss our method, which utilizes latent diffusion models. These models have become the benchmark for generative tasks because they can produce high-quality samples and adapt to various tasks through fine-tuning. The diffusion model learns to create images by first adding noise to them and then gradually removing that noise, allowing it to generate images from random noise. Unlike traditional diffusion models that operate directly on images, we use latent diffusion models that work in a compressed latent space, making them more efficient and scalable for higher resolution images. This latent space is derived from a pre-trained variational autoencoder, VAE. For any given image, we encode it into the latent space using the encoder of the VAE. During the diffusion process, we add noise to the latent representation based on a randomly chosen noise level. This process transforms the latent code into a Gaussian distribution. In the reverse process, a denoising network gradually removes the noise to recover the original latent code, which is then decoded back into an image by the VAE's decoder. We train the model by minimizing a specific loss function that measures the difference between the predicted noise and the actual noise. We enhance the latent diffusion models with conditional information through cross-attention modules, enabling us to tackle various tasks like generating images from text or translating images. In our work, we adapt a pre-trained latent diffusion model to co-generate depth and appearance for animating portrait images based on a reference image. For our task, given a reference image of the subject, we aim to generate both the appearance and depth of the subject across different expressions and poses. We model this as a conditional joint distribution in the latent diffusion U-net model. The final outputs are produced by decoding the latent codes for appearance and depth. The reference image is crucial for ensuring consistency in the generated outputs. To capture detailed identity features, we use a reference network to extract these features from the reference image, which we then incorporate into the latent diffusion model. In our approach, we generalize the latent diffusion process to manage multiple latent codes. We separately encode the appearance and depth, adding noise to each code independently. The denoising network is adjusted to handle both codes simultaneously. For simplicity, we combine the noised appearance and depth codes into a single representation, which the denoising network processes to recover the original codes. During training, the network learns to predict the combined noise, allowing us to refine our model effectively. Section Summary. In this section, we describe our method using latent diffusion models, which generate high-quality images by adding and removing noise in a latent space derived from a pre-trained variational autoencoder. We propose a joint learning approach to co-generate depth and appearance for portrait animation, leveraging a reference image to ensure consistency and employing a modified denoising network to handle multiple latent codes for appearance and depth. Section: Diffusion Backbone. In this section, we aim to utilize the valuable knowledge from a pre-trained latent diffusion model to learn our proposed conditional joint distribution, even with limited data. Since the original model is designed to generate only RGB images, we need to modify it to also produce depth and appearance. Our solution is straightforward. We expand the input and output channels of the latent denoising network. We initialize the new input parameters to 0 and duplicate the output parameters from the original model. This approach works well for us, likely because of the strong prior knowledge in the pre-trained model, which helps in generating good results. Next, we introduce ReferenceNet, which is created to improve and stabilize the generation process by using existing images as references. It has a similar layer structure to the denoising model, ensuring they work well together. Both networks generate feature maps that have the same spatial resolution and aligned characteristics, allowing ReferenceNet to effectively incorporate features into the diffusion model, enhancing visual quality. We initialize the weights of ReferenceNet from the denoising network and train them together. Our model is versatile and can be adapted for various applications. We demonstrate bidirectional prediction of images or depth based on the other signal, enabling tasks like monocular depth estimation and depth-based image editing. Additionally, we show that with extra motion attention modules, our model can generate portrait RGBD videos. For bidirectional prediction, our joint distribution of depth and appearance can be transformed into a conditional distribution in both directions. We achieve this through domain-wise inpainting in our jointly learned model. With a simple fine-tuning process, our model can generate images from depth and vice versa. Specifically, we use masked latent inputs and design different masks for appearance and depth during fine-tuning. For image-to-depth tasks, we set the depth mask to pure white and the image mask to pure black, and we reverse this for depth-to-image generation. ReferenceNet helps generate RGB images that match the reference image's appearance, allowing for applications like facial attribute editing and animation, which involve modifying the depth map using standard 3D editing tools. We will present experiments for both image-to-depth and depth-to-image in the following sections. We can also extend our model to create portrait RGBD videos by adding motion-related inputs and modules. For instance, in audio-driven portrait video generation, we incorporate audio and temporal feedback into the diffusion backbone with attention modules. We add an audio attention module and a temporal attention module in each block of the denoising U-net to capture speech-related motion signals and ensure frame consistency. We use a pre-trained Wave 2 VEC model to extract audio features for each frame and combine features from adjacent frames as audio input. To maintain continuity between sequences, we include the last motion frames from the previous sequence as input to the temporal module. This setup allows us to generate consistent portrait RGBD videos synchronized with the audio input. We will illustrate experiments on audio-driven facial animation in the next section. Regarding our experimental setups, the joint learning of portrait RGB images and depth takes about 3 days using 4 4090 GPUs. We use a batch size of 32 and a constant learning rate of 100,000, training our model for 30,000 steps. For the extended model with audio conditioning, we use a batch size of 1. The weights of the motion module come from AnimateDiff, while we keep the other parameters from the first stage. We generate 14 frames at once and use the first 4 ground truth frames of each training sample as motion frames during training. For our datasets, we train our model using a mix of data from both studio and real-world scenarios. We utilize a high-quality multi-view studio face dataset with images from 336 subjects showing various facial expressions, along with high-fidelity registered meshes. We create ground truth depth maps from these meshes to obtain paired RGB depth data for training. To enhance our model's generalization to real-world data, we include in the wild audiovisual sequences from selected clips of the HDTF and VFHQ datasets. Since these datasets lack corresponding geometry, we apply a state-of-the-art monocular face tracking method to estimate 3D geometry from the videos, allowing us to extract pseudo-ground truth depth maps for training. In total, we gather around 3 hours of video data from HDTF and VFHQ, consisting of 2,423 clips with diverse identities, facial expressions, and head poses. All videos are sampled at 25 frames per second, and the images are cropped to a resolution of 512 by 512 pixels. We also preprocess the audio to 16 kHz and extract per frame Wave 2 VEC audio features. This combination of studio and in-the-wild data provides a strong foundation for our network to generate high-quality images and depth across various practical scenarios. We will now demonstrate and evaluate the diverse applications enabled by our approach. Section Summary. In this section, we describe our approach to leveraging a pre-trained latent diffusion model to jointly generate RGB images and depth maps, adapting the model by expanding its input and output channels. We also introduce ReferenceNet to stabilize the generation process, enabling bidirectional predictions for tasks like monocular depth estimation and portrait RGBD video generation, while detailing our experimental setups and diverse datasets used for training. Section: Depth Estimation. In this section, we explore depth estimation, which has gained significant attention recently for predicting depth from single RGB images. Our model can effectively perform monocular depth estimation with minimal fine-tuning. We assess its performance using a studio dataset that provides accurate 3D depth maps, serving as our ground truth. This dataset includes 1264 images of 55 individuals displaying various facial expressions and poses. We adhere to the evaluation protocols from MIDAS and LDM3D, measuring metrics like absolute relative error, accuracy, and root mean squared error. To ensure a fair comparison, we mask out areas outside the facial skin region in the depth maps. We compare our method with leading monocular depth estimators, including Marigold, GeoWizard, and different models from the Sapiens Foundation model. Our quantitative results show that we outperform all other models, including Sapiens 1B. Qualitatively, our method captures facial shapes and expressions similarly to Sapiens 1B but with fewer artifacts. We also present results for monocular depth estimation on real-world face portraits, showing that our method produces better facial structure compared to a 3D morphable model, thanks to the depth correlation learned from our training data. Next, we discuss depth condition portrait animation. Our model allows us to generate RGB images by inputting a depth map, which is useful for precise image editing. We demonstrate this by modifying depth maps and regenerating corresponding RGB images, ensuring that the identity of the original image is maintained. We also highlight image relighting, where the learned facial depth aids in tasks like adjusting lighting in portraits. We use generated depth maps to compute surface normals for basic lighting changes, enhancing the final image. Furthermore, we extend our applications to audio-driven facial animation. Our network can incorporate motion modules and utilize audiovisual data for this purpose. We compare our method with other 2D audio-driven techniques, showing that while our RGB outputs are visually similar, we also generate aligned depth maps, adding a new capability not present in existing methods. Finally, we conduct ablation studies to assess the impact of our reference net on the quality of results. We find that removing the reference net leads to a loss of identity in generated images, underscoring its importance. We also evaluate the necessity of training on both studio and in the wild data. Training solely on studio data results in poor generalization to real-world images, while combining both data sources yields the best performance, as confirmed by our quantitative results. Section Summary. In this section, we explore our model's effectiveness in monocular depth estimation, demonstrating superior performance against state-of-the-art methods on a studio dataset, while also showcasing its capabilities in depth-conditioned portrait editing, image relighting, and audio-driven facial animation. Our ablation studies highlight the critical role of the reference net and the benefits of training on both studio and in the wild data for improved generalization and visual quality. Section: Limitations. In this section, we acknowledge some limitations of our method. While it is not restricted to just the facial skin area, it currently depends on depth maps from registered 3D geometry for training. This means it can only predict depth maps for the skin region when we input a new RGB image. Additionally, our limited computational resources have restricted us from expanding our training datasets and training durations to match those of existing audio-driven portrait animation methods. As a result, we believe that our current outcomes could be significantly enhanced with longer training on larger datasets.